Okay. Hello everyone. So starting a couple minutes early just to check the sound and video and stuff like this. As per usual, can you write in the chat does the sound work? Does video work? Stuff like this. Oh, I should have. Okay. So we have gathered here today to embark on a little bit of an adventure. So for people who are new, there's this project called Niagara, which has nothing to do with Unreal Engine's particle system engine. It is a renderer that is mostly written on stream. Last time, I think we did a stream last year, end of last year, where we talked about like geometry preparations and stuff like this. Today is going to be completely different. The one call out I would make is if you have watched the previous stream, at the end of the previous stream, we did a little bit of compression. And when we did this, I think maybe I said this, maybe I didn't, but basically, we compressed most of the scene data with like awesome mesh optimizers codecs, but meshlet data was not compressed because there was no codecs to compress it with. Well, now there is a preview experimental, things may break, etc. implementation of meshlet. Topology compression, meshlet, topology is the wrong word. Meshlet index related data compression, let's put it this way. It's pretty awesome. It's super fast to decode. I worked hard on it since December. It's reasonably ready, so I integrated it. The reason why I mentioned this is most of the code that we write on stream. This is a little bit of code that I didn't want to dedicate a whole section on stream. You can check it out later. It's a pull request that was merged a little bit ago. It's pretty simple. Anyway, so this is not why we're here today though. We are here today to talk about descriptor heaps and descriptors in general. VK success, great. So, last month, maybe, or this month, very recently, Khronos published the new descriptor extension, Descriptor Heap. This is a little different from the previous descriptor extensions, in the sense that when I talked to Khronos folks about this, and I think in their official messaging, it's like, okay, this is the descriptors of the future. Now, it is vkEXT, so it's not even a KHR extension, right? But I think it's because it's a very complex design space, and the extension is not that complicated, but with the previous extension, vkEXT descriptor buffer, there was a problem that this kind of was published, and then people figured out that it's actually not implementable in a performant way on some hardware, like NVIDIA's hardware. And so I think my understanding is this is designed to be this way you should work with descriptors in Vulkan in the future. But, just out of caution, it is EXT. So it is very fresh, which means it's not broadly supported in the drivers. I am right now running an NVIDIA driver, which there is an experimental version or a beta version or something like this of the NVIDIA driver that you can install that claims to support this extension. We'll find out today if this is true. And the latest Vulkan SDK has some support for validation for this extension. However, there is probably lots of caveats. This is like very new. Very quickly, this is the goal for today is to take our renderer and to change it to use descriptor heaps. Because this is a very, very new extension, ideally you would replace the whole like descriptor stuff with that extension unconditionally, and that could simplify the code. Unfortunately, today we are going to be complicating the code because I want to have support for the, I can't even use a production driver for NVIDIA card right now. AMD has a driver, probably also experimental, but because AMD in their commitment to open source stopped releasing open source drivers, you can't actually use it on Linux. I assume, or maybe you can, maybe there's a Linux binary, but it's like a proprietary driver either way. Radv has started working on descriptor heaps, but hasn't merged it yet. So, availability will be spotty. Because of this, we need this to be optional. However, the way the extension is designed, it's a little bit different from descriptor indexing. It's intended as a wholesale replacement. So when I say optional, I don't mean one of the draw calls uses this, although you can do this. But the goal for today, ideally, if we have time, is to replace, if the extension is supported, we dynamically detect it, and then we replace everything with descriptor heaps. Okay, so because it's going to be potentially a bunch of work with crashes and stuff like this, very briefly, why did people even make this? So if you look at the existing set of ways to make descriptors work in Vulkan, there's too many. In the original core API, there's descriptor sets and sort of descriptor pools and stuff. And then after this, they added update templates, which is an improvement sort of to a way you update descriptors. And then after this, they have added push descriptors, which is a way to which we use right now a lot. And this is similar to push constants, a way to just say, here's a bunch of descriptors for this draw call. The driver does some internal magic to make that work. After a lot of, turmoil, both of these have been added to core 1.4, 1.3 or whatever. There's also inline uniform block. Normally the way you work with constants is either through push constants or through uniform buffers. But if you have both of these kind of require you to upload this data, or if you use uniform, like every frame, or if you use uniform buffers, you can upload it once, but then on the GPU, there's an indirection on some hardware to kind of go from the descriptor that is representing the uniform buffer to the actual data. So there is an extension to put that in. And then there is the descriptor buffer, and then probably I'm forgetting things, but I think the major evolution is this. And then there's descriptor buffer. So there's descriptor indexing, but this is about, there's descriptor indexing too, and I think in some sense descriptor heaps also supplant that, although it's a little bit orthogonal. So there's descriptor buffer. I think it was released last year. The whole problem with the Vulkan model before the descriptor buffers has been that on most hardware, often on hardware, descriptors are just memory, and then all of these different Vulkan extensions try to mask the fact that this is just memory by sort of papering all of these different abstractions on top of this. Descriptor, and then also if you have a DirectX 12 application, it is working with the DirectX 12 descriptor model, which is heap-based, and converting from heap-based models to Vulkan models was annoying and difficult and had performance problems. So descriptor buffer was created to try to mitigate all of these things. And my understanding is on AMD hardware, descriptor buffer works great. There's no problems with descriptor buffer. However, on NVIDIA hardware and potentially on other hardware, descriptor buffer is too general. It hides too many things, or it presents an abstraction that is leaky in a way that makes it impossible for some hardware to implement it, even for modern hardware. Okay. And then also descriptor buffer, I think, could be used side by side with a bunch of other ways to do descriptors in a way that made it quite annoying for the drivers. And it has some other problems. So descriptor heap is supposed to fix all of this. So actually I'm on vulkangpuinfo.org site. As you can see, the adoption of the descriptor heap extension is quite low right now, which, it came out weeks ago. So the plan for today is we implement it as an optional thing, and then hopefully in a year or whatever, eventually it gets into production drivers, which should hopefully happen pretty soon, and then hopefully, I don't know what will happen, but if it ever makes it in core in some capacity, then we will just be able to remove all of the non-descriptor heap code, right? But for now we have to make do. So this is the plan. There is a little bit of, we had too many ways to do descriptors, so now there's one more way to do descriptors. Great, have fun. But I do hope it does seem like there's hope for basically applications in the future, like years into the future, to say, oh, this is the Vulkan descriptor model, and everything else that was there before, just forget about this. Okay. So, yeah, so I'm not, yes. Let's ignore Android for the sake of this. Let's ignore Android for the sake of this conversation. One caveat though. So, two caveats. So one is, unlike some of the other extensions, sometimes extension is introduced in Vulkan and there's an expectation that it supports all of the possible hardware that supports Vulkan. This is not an extension like this. However, this is an extension that should have broad support, at least on desktop, as in, I don't know how far back the support will go, but from our perspective, we are trying to work within the confines of like these modern ecosystems like mesh shaders, ray tracing, and stuff like this. If you are saying words like mesh shaders and ray tracing, and also if you are saying the words bindless, which is not all hardware that supports Vulkan 1.0 fully supports bindless, then you should expect that it's a driver update. But for pre-bindless hardware, I would expect that it doesn't get this extension. So this is why I'm saying, okay, it's like an extension of the future, in the sense that you can implement it today, you can't rely on this today, but once you can rely on presence of this extension in the drivers, you will have to abandon some older hardware to work with that. But such is life. Vulkan support, I think, is a little bit broader than DirectX 12 support, so it's to be expected. This is more similar to the DirectX 12 model. Okay. Finally, I won't talk any more about the hardware details, but there's an excellent post by Faith Extrand. Descriptors are hard. This is actually from years ago. There's no date on this. I think it's from 2022. Yeah, it's probably from 2022. So there's an old post that talks about hardware models for descriptors. And there's like this beautiful table that says, okay, for this type of hardware, this hardware works with the given model. And broadly speaking, Vulkan 1.0 through abstractions can support all of the letters. But the important sort of hierarchy, I guess, is that so D, B, and H, I think, should be supportable by the descriptor heap extension modulo, potentially some complications that I'm not aware of. So H is literally heaps, which, so B is descriptor buffers, but I think it's like just less restrictive than heaps a little bit. And then D means direct access, which means the shader loads descriptor data from somewhere and then passes it to the instructions that actually use this descriptor data. And D is the most general in some sense because the shader can load data from memory. And so descriptors, but the general notion behind all of this is descriptors are just bytes. It's just that direct access says these bytes can come from anywhere. The shader figures it out. Heaps means descriptors come from a given kind of thing in memory that has some restrictions on placement or whatever. And B is some middle ground. But in Vulkan 1.0, there's also hardware that uses fixed hardware bindings. And fixed means you can't do descriptor heaps, pretty much. And so this is actually a good, if you look at this, okay, so NVIDIA's newer hardware is heaps. AMD's is direct access, which means you can do whatever. Intel is heaps with some complications. Intel pre-Skylake is DOA for this extension, right? Like, nobody's going to implement it. It's probably impossible. ARM newer hardware probably is implementable. ARM older hardware definitely isn't. Qualcomm and Broadcom might be fine, right? So, but this is the optimal picture. A given vendor may decide, oh, there's some specifics of this extension that still don't play nice with some of our hardware, so it's going to be like a more bleeding edge thing. Anyway. read this post if you're interested. Okay, I was trying to speed through this because we have a lot of code to write, and you know, ideally I want to make it happen like this stream without splitting into 2 streams, but if we run to showstoppers or if it takes more time than I am thinking it might, then you know, it will spill over. Okay, so. Yeah, the beta driver is the beta driver. So I'm not sure about Molten VK, and I'm not sure about Cosmic Crisp, which is the spiritual successor, I guess. So Cosmic Crisp should be fine because Cosmic Crisp relies on Metal 4, I believe. And Metal 4 is more general than any of this probably, so it should be fine. Molten VK, I'm not sure if they have plans to implement it and stuff like this, so I don't know, can't speak to that. And yes, the driver that we are using right now is 58094. It is interesting because the latest NVIDIA driver, official driver, is actually 590, but the beta one is kind of based on the older official driver, but it has these bits that the newer driver doesn't have yet. So I'm expecting all of these things to stabilize in the future, but kind of this is what we work with right now, right? Okay, so to remind people where we are at, we have this beautiful renderer that you can run. I'm running this right now in Debug, but the load was pretty fast because of the work that we did last stream to cache the scene load and stuff like this. Debug means we have assertion, we have validation layers, we have like all of the things. So, you know, you can like move around, the shadows are done using ray tracing, the rasterization is responsible for actually drawing the scene. We have mesh shaders with occlusion culling and all of this sort of cool stuff. So the goal is to get all of this running, ideally, hopefully. I don't know. We'll see. So there's 2 ways to use descriptor heaps. I'm going to be referring a lot to this proposal. I read it a little bit. I haven't never tried to use this. Obviously, this thing is super new. I briefly read all of this, but I'm probably going to be missing details and stuff like this. We'll find out. So generally speaking, there is 2 parts to this extension. One is you allocate buffers within which your descriptors will live, and you decide where to place these descriptors because it's just a buffer, it's just memory. The extension tells you how big the descriptors are. Crucially, unlike descriptor buffer, this extension makes a split between samplers and non-samplers, and we'll have to deal with this. So there is a sampler heap and a resource heap. Sampler heap supports samplers. A resource heap supports everything else like buffers, images, whatever. I'm not sure. It will be unfortunate if you have to do something weird with acceleration structures, but hopefully it's going to be fine. Okay. So you allocate buffers, and then you have to teach your shaders, and then you bind these buffers. But there's only one binding for a given heap. So think about these as global resources, and you can switch them mid-frame. The extension or the hardware, some hardware really doesn't want you to. So think about these as this is a thing you set once per command buffer, unfortunately, but you know, whatever. Set once at the beginning of your command buffer and just forget about this. And then you have to tell your shaders somehow to fetch data fetch descriptors from this heap. So forget about descriptor sets, forget about push descriptors, forget about, you know, everything that you've used before in Vulkan, because nothing is automatic for you. The only thing you still get is you get push constants, but push constants go through a slightly different API. So none of the existing Vulkan calls basically are compatible. And in fact, if you look at some notes, so if you use the new extension and the old extension and the old ways concurrently, they will overwrite each other, meaning it kind of ideally has to be a full frame conversion, because if you can render Drawcall without using descriptor heaps by setting up all of the state, but then you have to rebind the descriptor heaps again, and that can be very costly on some hardware. So ideally, it's a full frame conversion. So this means we can't use any of the code that we are using right now, but I'm hoping to use a similar paradigm where we have push descriptors that we'll have to implement ourselves, and we have other stuff that we also have to implement ourselves. I think in general, the notion here is the driver does even less work, and so you have to do even more work, which, at least the work that you do is closer to hardware, so that's cool. Like there's less abstractions in the way, but some abstractions were helpful in reducing the amount of work that you have to do. So, okay. So when you teach your shaders for how to use this stuff, there's two ways to do this. One is you can directly start working with indices into these descriptor heaps. Like you say, or it's byte offsets usually, but it's like, okay, this image, I know it lives here in the descriptor heap, so I'll tell my shader to read directly from this. And this is fine. However, the goal for today's stream, remember, is to maintain the old path, which means we can't really change the shaders, or if we change the shaders, we have to change them in minimal ways that are still compatible with how we used to do stuff. So for this, thankfully, the extension provides this extra thing, which is mapping, which is when you create a pipeline, presumably. When you create a pipeline object, instead of telling the driver the descriptor set layouts, there is no descriptor sets anymore, but you have to tell for every descriptor binding in the shader where will it come from. And there's a bunch of fun modes that you can look at in the extension. Basically, all of these boil down to how does the shader compute the offset in the descriptor heap from the source data that you give it. And there's a bunch of options here. We will use a couple of them. Okay, so that is kind of the plan. So we have to create the heaps, we have to bind them, and then we have to change all of the code that binds descriptors and push constants. And we have to also change the code that creates the pipelines to kind of teach the driver where to get these things from. So we're going to try to do this. Hopefully it's not going to be, that bad. We'll see. And hopefully we will not have too many issues. The one unfortunate property is this extension is more difficult for tools to implement. Validation layers supported. However, support for synchronization validation is more limited. I don't know that RenderDoc, I mean, it's been like a week, so I don't know if RenderDoc supports it yet, but basically there is going to be kind of issues for tooling availability around this extension, I would assume. But because we have two paths, going forward, we would have for some time a way to disable the descriptor heaps and then see if things still work, and then eventually we'll get rid of the non-descriptor heap code. Okay. So that is kind of it. Let's start writing some code. I will try to, I don't know if this spec has examples. It has examples of mapping. There's a bunch of boilerplate that's not interesting. And there's some other stuff that's, okay, it has very minimal examples. Okay, that's fine. One thing I forgot to mention is how do you get descriptors? So this is a little bit similar to descriptor buffers. There is a separate function, actually this one, that you can use to convert the resource info into a descriptor, and descriptor is just a bunch of bytes, and then you decide where to put these bytes. It's a little different. It supports multiple resources in one call. Also, unfortunately, so back to this XKCD comic, this extension doesn't use a bunch of the kind of previously available functionality from the core specification. Specifically, doesn't use view objects. On one hand, this is nice because you don't have to create them. On the other hand, the view objects encapsulated stuff about the resource that's now not encapsulated. And you kind of have to do more work. And in our case, because we still have to create the image view objects and buffer view objects for the old path to work, it's kind of even more work. So, again, if you were doing this from scratch, things would be easier because you could design or not design even, but like you wouldn't have to implement the old stuff, but we have to. So for example, when you specify the image descriptor, so to get the image descriptor bytes from the driver, you have to give the driver information about the image, and the information about the image is literally the same thing that you have used to create the image view in the first place in the older, in the older like paradigm. And then for buffers, I guess it's just an address range. So it's literally just device address, like the GPU address that the buffer corresponds to. Fortunately, we already have added in the past support for buffer device address. So hopefully this will be not too bad, but we'll see. Okay. I think that's kind of it. I think that's kind of what it is. So yeah, okay. I think we can start writing code. Yes, it has to be a development beta driver. Yes, yeah, I know Sasha Williams published an example. I think it's like a simpler sort of, here's a specific shader that we, it makes sense. So consult the example if you want to follow along, sort of, if this is too confusing, then the example would be great because it will be easier to follow. But I want to do some things in somewhat specific way, and I don't know. I only skimmed the example code. I don't know how exactly it approaches these things. Okay. Anyway, so we have the beta driver. We should have the extension available. So the first thing that we need to do is to enable that extension. But we need to do this optionally. Okay. Yeah. Let's call it desk heap, so that there is a consistent name. There's another weird thing where I will try to remember to do this everywhere, but all of this stuff is bleeding edge, so you need the latest headers and the latest SDK and stuff like this. I have all of this installed, but we might use ifdefs for a little bit to make sure that you can still compile the code on all the headers, although we won't like check it, but just in case. Okay, so if it's supported, then we need the extension in the extension list. And then I'm sure you have to enable it. So let's see. So this is descriptor heap features. Okay. And then I have no idea what the struct actually contains, so let's look at this. Okay, so you just have to basically say I want a descriptor heap functionality, which makes sense. Or it's annoying boilerplate, but Val can spec like this, so that's what it is. Okay. And then here, wherever we have other supported booleans, we will do the usual thing where we check support for this extension. It will be funny if I typo in one of these. Okay. Okay, so then we will print something to ext descriptor heap support code is being used. Sort of, I don't know. Let's just leave it as a warning. The reason why I want to print a warning here is A, I want to see a printout. B, this might have bugs. We will test on one driver. All of the code that we have had here so far has been tested on like 3 drivers. 4 drivers from three vendors. Who knows if, you know, who knows if this code works? Who knows if this code is correct? Okay. Okay. I see the printout. This might be obscured a little bit, but that's fine. Okay. So we have initialized the extension, and validation layers are enabled. So that part was easy. Okay. So now we need to create the descriptor heap. So I've thought about this a little bit offline, and the way we are gonna use this extension is as follows. We are gonna create 2 heaps, obviously, one for resources, one for images, or one for samplers. The heap for samplers has to be separate. This is the hardware restriction on some hardware. So the way we are gonna approach samplers and everything else is a little bit different. We are gonna have the sampler heap we use 3 samplers right now, and we'll just put them in the heap, and we will just do some stuff to like make sure that the shader knows which one to read. So technically we need like 16 at most. And then the resource descriptors, we will split into kind of 2 parts. You can think of it as static, as dynamic. It's not quite the correct description, but basically we were already using descriptor indexing to have all of the textures that we load from the file in like one sort of one array. And we will use that for, we will use the static portion of the heap for that. And this is going to be our bindless, quote unquote, sort of segment. And then the other thing that we'll do is for every frame in flight, we will have space for push descriptors, for descriptors that are submitted dynamically. And that will have to multiply by the number of frames in flight, and this is going to be kind of our total like frame, our total descriptor heap. And then the other thing is, so buffer descriptors and image descriptors can be of different sizes. The extension gives you freedom to allocate them like optimally. I'm going to ignore this and just assume every descriptor is the same size and just use the maximum of the 2 sizes, just because it's simpler right now and it's not that important. This is not optimal on all hardware, obviously, but you know, probably it's going to be fine. So this is going to be the simplification. So submitted per frame via push, and then maximum number of sampler descriptors, and this is going to be resource descriptors, and resource descriptors allocated statically. Okay, so that is the plan. So then we need to create the heaps. I guess we can do this here because we do all of the other stuff here. I'm not actually sure. So let me look at the heap management. So you need, oh, you just allocate memory. There's no object, right? That makes sense. Okay, okay. So I think we will. Okay, right. This is where Sasha's example would probably make things faster for us, but I like figuring some of these things out. So I think the notion is that when you create a resource heap or any heap, so I already said that we are expecting to like allocate things in a specific way, but the other thing that you should do is reserve some space for the driver to live within the same heap, and the driver should tell you how much, oops, sorry, how much space to reserve. Okay, let's see. So you can query the properties from the driver. This will tell you the sizes of the like resources of the descriptors and stuff like this. Oh yes, this thing. So you are supposed to give the driver at least this many bytes for sampler heaps, and presumably there's, yes, and this for the resource heaps. Okay, so let's actually start with that. Actually, it's like the first thing basically that we'll need to do, so we might as well do this here. The preprocessor stuff is gonna be like easy. You know what? Let me ignore the preprocessor macros for now, and then once we get the code working, then maybe we can go back and like put them back in, but it's too much kind of context switching. Okay. And then all of the usage again at runtime will have to be like checked. Like we can only use all of these APIs obviously if they are supported. Oh, I haven't updated Volk to the version that actually supports this extension. We will do this in a second. Okay, so we need to get the structure. Where's the function that gets it? Oh, it is get device properties. Is it this guy? Is it changed to this thing? Dear God, people. Okay, all right, fine. Okay. I'm assuming it's changed to this thing. Yeah, it must be. Okay. Wait, but this thing doesn't have pnext. Oh, there's there's this guy, right? Okay. All right. Okay. I swear this API sometimes. Okay. All right, so we need to get the properties. We need to get the properties using this newer function. And then this guy will just be here. Okay, wait. And then that gives us an ability to chain this second structure to the first structure, and now we will actually be able to get to print, you know, things. So let's print the sizes, and I guess let's print the reserve ranges because this is the thing that we will need. Does this thing not have an error code? I guess not. Okay. So and then hopefully we can use the amazing power of autocomplete to backfill all of this nonsense. Okay, let's see if that worked. Okay, that worked. So I don't know that you can see. Now you definitely can see. So we have sampler descriptors are 32 bytes on this driver, image descriptors are 32 bytes, buffer descriptors are 16 bytes. So when I said that we are gonna kind of use the larger of the two to just pretend that resource descriptors are the same size, we're gonna lose a little bit of effective sort of memory, but we'll just ignore all of the kind of deep efficiency concerns for now. And then for the resource heap, we need to reserve like 100K of space for the driver. And then for the sampler heap, we only need to reserve 500 bytes of space. Okay, so now that we know this, we can actually sort of create the heaps, right? Because now we know how many resources we need. We know what types they should be and stuff like this. And actually, we don't even need helpers for this because we have this function create buffer. So we can say, okay, so we need the resource heap, and we need the sampler heap. And if the descriptor heap is supported, then we just need to create the buffers, and we should have like a function create buffer for it. So we know the sizes of these buffers. there should be a property flag or a memory like flag or something like this. Let's go back to this thing. So this is binding. Yeah, so there's a buffer usage that indicates that the buffer will be used as a descriptor heap. Oh, right, the memory properties is just the thing that has all of the heaps. Okay, perfect. So then basically we just need to create a resource heap on our device using memory properties that we probably get later. So we need to move that thing up. I could move the other stuff down, but I think I'll need some of these properties for creating the pipeline object, so it's easier to do here. Oh, but the properties I got. Yeah, okay. Let's actually create all of the resources where we are creating them right now, because that's going to be more kind of coherent. So here. Okay, so we create the buffer resource heap device memory properties. So then the size for the resource heap is going to be, as I was saying, so we need descriptor. Okay, I don't know why it complete doesn't work, whatever. So max frames plus descriptor frames. Descriptor limit frame. And then the sampler descriptor count is just the preprocessor constant, right? Okay, so then when we're creating read resource heap, the size should be, and there's some things with alignment that get a little bit weird. I'm just gonna ignore them for now. I'm sure the validation layers will complain at me later. But, okay, fine. You know what? Hold on. Actually, no props, discrete properties. So as I was saying, the effective descriptor size that we are going to be using for resources is going to be the maximum of image and buffer. Yeah, you know what? Okay, I'm going to ignore the alignment stuff. Things will explode. That's fine. So we need enough space for the descriptors that we store. Plus, we need this reserved range. This guy. All right. So then we need the usage flags, which are effectively this. And there's a little bit of an interesting problem with the device addresses, because we'll need them like on all of the buffers, I think. And I think right now we might only be capturing them on some of the buffers. Okay, I'm going to think about this separately. The other thing is, so we'll allocate this resource buffer, but then we'll need to write resources to this. I don't want to deal with, so I want a host visible buffer, meaning I want to be able to write to this buffer from the CPU, because otherwise you have to schedule like additional transfers and stuff like this. I don't know what part of this is like guaranteed to be supported and what part of it is not. So it's possible again that the code that we're writing right now is like naive in some way. Samplers times disk heap properties samplers is okay. Okay, so we create the buffers. I'm gonna do there's a device address thing that I need to think about. Yeah, okay. So actually this is what the validation error is about too. So here's the problem. So we can like specify the flag, this part is easy, but the problem is every buffer that we create, for it to be bound to the shader, it will have to have the device address bit, because like, uh, you know, there's no buffer view anymore. So because of this, I think we'll base, and you have to require buffer device address, obviously. Um, you have to require device address. So like device address is necessary when you use this extension. The problem is when we create the buffers, we don't even pass the flags that would tell us whether we are using descriptor heaps, and I don't want to change all of that code. I think it might be time to just start hard requiring buffer device address. Because it's effectively required. I don't know if we know that we can use it, as in I don't know if the Vulkan specification says that it has to be supported from like 1.3 or 4, but effectively we will need it, and it's going to be easier to just always assume it's there. So basically let's just do that. Okay. Maybe something else will explode once we do this. No, okay, that's fine. Oh, right, we have to destroy the heaps, obviously. Okay, so we created the heaps. We all know, well, we kind of need the reserved range because we'll have to specify this. But that's fine. Okay, so then, like at the end, wherever we destroy buffers, here. So see, on one hand, not having to sort of not having all of these views and things like this is simpler conceptually, but on the other hand, I guess we create them like this. On the other hand, this means you have to track more information now, which can be annoying. Okay, so now that we've done this, I guess I can just go ahead and put leave defs. Oh, that's going to be messy. Okay. Okay. No, you know what? The if defs are, the only reason why I'm doing if defs just so that you can compile the code for earlier headers. This might be a fool's errand. It might be easier to commit to this, but if we decide to commit to it, we can just remove the if defs. Okay, so now we have created the buffers and we have destroyed them, but we have done nothing else. So obviously we are very far away from done. The one thing I want to do is I want to try to bind them, just to see what happens. And I think in general, when I thought about this, so at the very end of the frame, if you see when we run the code, there is all of this text that you can like read that displays various information. This is at the very end of the frame, and it's rendered by a compute shader, and the compute shader needs to write to the swap chain image, but has to do nothing else. There's no samplers here, there's not even buffers, and it uses push constants to get the data. So I was thinking the first step would be so I was saying you kind of should replace the whole frame, but you can replace the whole frame one draw call at a time as long as you rebind like the descriptor heaps, which is bad for performance, but it's good for actually iteratively developing your code. So I figured the thing we should do is do that for the Debugtext, and then we could move the thing like, you know, a couple steps by a couple steps, like to apply to later parts of the frame or earlier parts of the frame, and then at some point we'll just like do this unconditionally. So let's do that. And that will exercise the binding code, which will hopefully catch whatever we are not doing correctly, sort of right now. Okay, so we need to bind both heaps. vk structure type bind. Bind. Is it the same? Oh yes, okay, got it. Okay, so it has the address range and also the reserved range. For some reason, the reserved, oh, because it's the range within the, okay, that's kind of strange, but whatever. So the address of the heap is whatever we have allocated it. I think we have a get buffer address function, which actually, the more you go into this, the more kind of things you decide you may want to cache. We used to not cache the buffer addresses. It actually would be good probably to start doing that, but that's fine. I think we have a get buffer address function, don't we have it? Yes. So buffer and device. But for now, let's just, I want to be tactical about this to the extent I can and not rework things unless I know I have to. So that is the plan. Okay. So then the size is just sampler heap size. Although in this case, it would be easy and probably beneficial to just cache the thing. Now that we are unconditionally grabbing it, it probably would be good. But okay. So, I guess we can place the reserved range either at the beginning of the heap or at the end. It kind of doesn't matter one way or the other, but it's probably easier to do this to place it at the end. I'm just not sure if there's any alignment considerations or whatever, but it's probably fine. So, desk heap properties. In theory, the driver can do something stupid like, you know, oh, like we need this memory to be aligned by 1 kilobyte, but we only need like 17 bytes of it. So I will return 17 bytes and alignment separately, in which case you kind of have to align all of these things manually. We will not bother. Our goal is to get the thing working, and then we can consider, you know, did we do the right thing? Oops. Etc. That can be a separate consideration. So sorry, the text is jumping around. I'm kind of used to this. This is how auto-formatting flow works, but this, I realize it might be confusing. Okay, so we bind both heaps, and then we get an error. Huh? Why do we get an error? Oh, right. So this is the point where we need to update Volk. So Volk, as usual, has support for everything whenever it's like released. So hopefully this should be fine. I lied. Why? Hold on. Oh, hold on. There's the. Okay, I'm confused. Okay. All right, cool. Okay, so now we are binding the buffers. So we've updated Volk. Now we are binding the buffers, or the heaps rather. But in theory, so you bind the heaps. This invalidates like everything that you've done with other stuff, with like Vulkan 1.0, etc. But after this, we bind everything again. So in theory, this should still work. It's just the binding will be redundant. Let's see if that's true. So we asserted the buffer was created, right. So what I meant to do when I was enabling the buffer addresses was to always require it, obviously. So we kind of need to set this vk buffer usage shader device address bit. Okay. Okay, so everything still renders. There is no validation errors. We have done nothing interesting. We have just bound the descriptor heaps, but we are not using them. So obviously nothing, nothing is broken yet, and it's good. All right, let's actually use this opportunity because, yeah, I decided we should probably cache the thing anyway. And then we can leave a to-do comment for ourselves. Okay, to-do replace this with direct access to buffer address. We will not actually do this yet. But here we will actually, we can just do this, right? Is it the second, the first? Okay. Okay, it's a little circular, but it's fine. Okay, and now we don't need to be calling get buffer address here. We just have readily available access to the buffers. Okay, cool. So this concludes hopefully the heaps. Now the problem is we need to actually start using them. It would be easier if we can convert the fixed portion first, like the bindless access that we use right now, because that's going to be easier to do, but unfortunately that requires that shader needs push descriptors too. So basically we now need to implement push descriptors. Okay, let me just briefly look at chat. Okay, thank you. So buffer address should be good. Are descriptors heaps better than bindless descriptors? Oops. You can kind of think of descriptor heaps as like the ultimate bindless, in the sense that the bindless before this was kind of like hacked in like odd ways. Descriptor heaps give you true bindless. Like there's a GLSL extension with descriptor heaps that you can use to literally directly read the resources out of descriptor heaps. And it's actually great. It's just for us, it would mean committing to descriptor heaps as in not having a fallback path. And we can't do that yet. But yeah, I mean, it's like better in the sense that it's like full bindless, full bindless. There is no more bindless. See, the only thing that we are going to be binding here are samplers and resource heaps, and we have already done this. This is the last binding call in our code. Doesn't mean we are done, but okay. So the next step actually then is this. Let me wrap. So we have in many places we have direct calls to vkCmdPushConstants or vkCmdPushDescriptor set with template. this is going to be problematic for us because in every place like this, we'll have to either use this, or if we use descriptor sets, use the descriptor heap based, or descriptor heap, sorry, descriptor heap based stuff. So I want to wrap this in a function, and we actually already have a similar helper that combines the two. So I want to like, basically don't worry about this. This is just going to be calling the same Vulkan function for us. So this is like this, and then most of the rest of the stream is just going to be like making these functions work. So push descriptors, program, descriptor info, push descriptors, push descriptor count, and then we can just do this unconditionally. That's fine. Okay, and so now whenever we had push constants, I want to replace it with push constants. Is pass data. Oh, right. Yes. Okay. So this is going to be easier anyway, as in it's going to like simplify the code. Okay. So for people who are wondering, the editor is Z-E-D, and also, as somebody observantly noted, I have switched to a new desktop setup and I really like it. So this is, I'm still using Ubuntu Linux, but this is Niri compositor and Dank material shell, something, the desktop environment, which is like the bar at the top and stuff like this. I was getting annoyed with some GNOME stuff around just, I like switching between I like using hotkeys to recombine my, like, to switch between windows, to tile things and stuff like this, and I was using all of this in GNOME, and GNOME is really not made for this, and so I was curious about Niri, and I tried Niri, and I really like the combination of, it's kind of tiling, but kind of not. Tiling always felt more restrictive because it kind of randomly resizes your windows, and Niri almost never. Niri basically, like, every window resize is intentional. Anyway, I just, and also the default setup that they have with the material shell, it's like one command on Ubuntu to set it up. And I had to fix configs a little bit, but it's not too bad. And the result is great. So, you know, if you use Linux, highly recommend. Okay, so we have an assertion, which is interesting. So we messed up something. And I actually don't know what we messed up because I need GDB to find out. Okay, fine. All right, refactoring almost successful. I think somewhere I messed up. Maybe it was a place where there was descriptors 2. Oh, there could be also a case where the shader like doesn't use some of the descriptors. That would be kind of strange. Let's see. So in line, what the heck is line number? 146. 146. Interesting. Huh? Interesting. Okay. The side effect of some of the stuff that we're going to do, by the way, is that we're going to move some of the validation code into assertions, which is sort of good because it will force us to be more, to have more robust code, but also we'll have to debug some stuff. So we have 8 descriptors, but we are pushing 9. I think this might be because the shader doesn't use them, and so we have to assert like that we are providing enough descriptors. Let me double check this so that what is cluster pipeline, cluster program, meshlet mesh. Okay, fine. What is MTB that it referenced? I do not. Material buffer. Why would you not reference the material buffer? That is strange. Hold on. That is strange. Huh? Mesh fragment shader. So this is the buffer. Why would push descriptor count? Oh, is it because there is one that's skipped? Is push descriptor count lying? Like it's not. Oh, that can't possibly be right. What is this guy? So this is like 6. Huh. Five, 6, 7, 8. What was this thing even supposed to be? Oh, this is probably like in the task shader. Right, this is the depth pyramid. So the depth pyramid is absent. This is fine. Wow, I'm confused. Why would push descriptors be 8? Huh. That is quite strange. Let's see, push descriptor count. Yeah, it doesn't count the right thing. It's like the number of descriptors used, which is basically never relevant. What you want is the maximum number. Why? How did this even work? Do we never use this other than for asserts and it just happens to work? Is that what it is? Yes. Okay. All right. So this is good. We found a small bug. Let's just move this here. Okay. Track descriptor count, including gaps. Okay. 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 All right. Disaster averted. So now, now that we've replaced, like now that we are not calling, we are still calling bind descriptor sets like in a couple places manually, but that's fine. We'll replace it later. The thing that we need now is we need a way to implement these two functions and sort of these function as a byproduct. In fact, here we can delegate because it's doing okay, cool. I don't know, man. All right. Okay. So this way, and then here. Okay, so now we just need two functions that we need to implement. How hard can it be? So it turns out that it can be pretty hard because we'll need to change a bunch of stuff. So the thing that we need to do to prove that the whole thing even works is to make this shader work. This shader uses push constants, which is very simple. There's a different API that you call in this case, and you're done. But it needs an image descriptor, which we want to be using the push mechanism. And implementing that requires some work. Oh, and I also realized so push descriptors, to make push descriptor work, it will need one piece of global state, which is like the current offset. Not using any C++ is getting a little annoying here in the sense that we need, okay, so we'll need like a struct that essentially tells us the state of the frame descriptor objects, because what we are going to be doing is we're going to be writing descriptors to an offset in the descriptor buffer that will be based on the current frame index and also the how many we have already consumed, so to speak. So we'll need the struct, let's call it frame descriptors, and we'll need to pass this struct like everywhere, where we select to push constants and push descriptors basically. And that is gonna tell us and that will tell us the descriptor offset within the heap that we can use for the frame stuff. And also we kind of need to know if we have enough space just to be able to assert and say you can't write past the sort of frame descriptor buffer. So unfortunately we need this thing, and unfortunately we need it literally everywhere. So well, let's just add it, I guess. Let's call it frame desk. Okay, and then we have a whole bunch of compiler errors to fix now. So whenever the frame starts, let's look somewhere here. Yeah. Okay. And then the setup here will actually be very simple. We'll just start by saying we know the frame index, we have reserved a given number of descriptors statically, we'll never touch that. And then every frame has a certain number of descriptors that it's allowed to access, and that is it. And then the end offset is just like we can use up to the limit frame descriptors in the given frame. So that is it. That is very simple. And the only annoying part is like passing this this thing everywhere. Okay. Let's try to do it like this. Okay, and then there was push constants. Okay, and then we had dispatch somewhere. Not actually many, maybe we can just do this manually. This is the stuff that the driver was doing for you. Like pretty much all of the code that we are writing now, there was code in the driver that did something like this. And now we are responsible for this, so. Okay, All right, so we are almost ready to start writing the actual code. However, the thing that we haven't answered yet, the question that we haven't answered yet is, how do we get the descriptor data? So for buffers, I forgot. Oh man. So I had a plan to cache the descriptors in the buffer objects. Oh no, never mind. You don't. No, you do need this, yes. So you need an address. Oh, things are not easy. Okay, let us not cache descriptors for now, or yet, I should say, and then see how far we can get. Things are annoying a little bit. Previously, descriptors inside the driver were kind of associated with the image view. I thought I could, yeah, hold on. So the thing that we are using to push descriptors right now is this structure that that just stores view objects. Because we can't use the view objects now, we have to pass additional data when we initialize the descriptor infrastruct. Unfortunately, or maybe fortunately, so the buffers are actually like more straightforward than images, because for the images you need the things that you use to create the image view. Let's look at how we create the image views to begin with. So we use the image, we use the format, we specify the format. I wonder if you can like use unknown format somehow. Let's see. So essentially, we will need to fill all of these structs. And it's a little annoying to fill all of these structs. And we fill these structs when we create the image views, but now that we can't like extract the thing from the image view. And we sometimes use image views that span the whole thing, and sometimes use it for an individual MIP level. So I mean, I guess one option is to just force the caller for now to pass all of this stuff manually when you... The format is kind of nonsense. I wonder, so okay, so when you create the image view, can you say, I don't want to tell you what the format is going to be? I bet the answer is no. I bet it's gonna be annoying. Oh my god. Okay. All right, fine. So let's do it like this. Do we even have the image struct here? We don't. Because like it's also forcing us to couple the different portions. Oh, the image struct doesn't even have the format here. Okay. All right, cool. Yeah, so it would be more straightforward if you could just pass the image descriptor like memory to the descriptor info. All right, I'm strategizing on the fly. Okay, let's hack it together for this one case just to get a feel for what it's like. And then hopefully that will mean that we actually can get like the rendering code working. And then we'll see how to how to like make it so that we can easily replace it everywhere in the code. Because the thing here is we only need the descriptor for the swap chain image view. We know the specifics of how the swap chain image views are created. We can just like plug things sort of manually somehow. So let's maybe do that. But also I wonder if I should. So you can like delegate the responsibility of filling the descriptor data to the descriptor info, or you can have descriptor info just track the resources that it kind of originates from, and then Okay, so I have to fill. Let's look at the image views. It is ironic because if they didn't remove the image views, we would not have this problem. If you could just use the image view to get the descriptor, but you can't. So we have the swap chain image views. We create them from the swap chain. It's a swap chain format. It's 0, 1. So, okay, let's start by just writing a couple helpers and then we'll figure that out. Let's just have a function getDescriptor that fills the descriptor memory. I think descriptors are up to 128 bytes in the spec. Let's just do that for now. So given a device, given an image object, given the format, and basically all of the other stuff, like give me the descriptor. And then let's do the same for buffers. Given the buffer object, and technically you can just do this based on device memory, but I guess, sure, let's just do that. Address, vk device, size, and then the same descriptor thingy. I think image descriptors are technically up to 64 bytes, and buffers are up to 128 bytes. We could also like have a constant somewhere, it doesn't really matter. Let's just write some code and then see how it works, and then, because I don't have a great feel for how this thing should work yet, so it's a little difficult to kind of organize the API in the best way. And so we are not going to be using, you can like do this multiple descriptors at a time. We are not going to be doing that. Right, resource descriptors. But yeah, I just want to like call the function and see what happens basically. So this is device, resource count, and then you need this stuff. Okay. Device, resource count, resource info, and then descriptor range. Why is there a range here? Interesting. Okay, fine. Okay. I'm not sure why it needs a range just to do the bounce check. It's kind of strange. Okay. No, descriptor size. Is this just void star? Yes. Okay, thank God. Okay. So then we need to fill this beautiful structure. And then it has the type. So the images are just, oh boy. Yeah. So the images have two possible ways in which you can use them. One is sampled and one is stored image. And the descriptors are different for these. So you have to specify this here too. Let's just do sampled, I guess. Oh, and we'll need this. Okay, let's just do the key descriptor type. I would imagine that maybe this is similar for buffers, but maybe it's not. I'm not actually sure. Let's pass it through for now. Yeah, I now doubt we will actually get there by the end of this stream. All of this is not difficult, but it is fiddly. Like it's not like inherently, oh, we are doing something super hard, but it may be a while. Okay. So okay, so we don't need texel buffer and we don't need ARM tensors, so we really only need these two guys. So this buffers are really straightforward. You just have an address range and you're done. Images, you need this image descriptor info, which presumably has like vkNext and stuff, or S-type vnext and stuff. Yeah, okay. And then you specify the view and the layout. The layouts, at least the layouts are very simple because we have switched to general layouts like a couple streams ago, so there is no way to communicate that. And the view create info is the thing that we actually have to fill. Okay, okay. This could be worse. Could be worse. It's still not great. So primarily, I think the big thing, that would be easier is if we could just assume that that we can use the image, that we can use the descriptor heaps unconditionally, because then instead of like maintaining two paths, we could just kill the old path. But that is not in the cards for now, so we have to persevere. Is it like the address range, and here it's resource info data p image. Okay, okay, let's call this stuff like on a couple objects that we have and see if it actually works, and you know. Okay, so we now have this beautiful function getDescriptor that you can call and pass decidedly too many arguments. So let's actually do this for the swap chain. Swap chain image, swap chain index or whatever. image index, swap chain format, mip level, level count, that specific. I'm actually confused. Hold on. Is there a difference between storage and sampled? When you create the view, you don't tell it. Why would you tell here? Huh. Interesting. Oh, I guess the image view can internally store both types of descriptors. I think that's what it is, probably. Okay. Descriptor, and then desk heap properties, image descriptor size, and then I don't know. Okay, and then let's do the same with like a random buffer object. So to do this on a buffer object, we don't need any of that. We need, hold on. Right, and you have to tell it uniform buffer or storage buffer when you create the buffer descriptors. Okay, okay, yes, so we need the descriptor type. Yeah, okay, so the descriptor info thing is going to be painful. We can't even, we have to specify way more data than we are specifying right now, because way too much stuff was like inferred. I think that means the descriptor info will have to track the source, like where the data comes from, because it's too much typing to, like every time you use a buffer, the shader knows which type of buffer you're using. Okay, so that clarifies this. We will do that. There is still a weird compile time dependency, but that's fine. Okay. Which buffer are we interested in? I need a buffer. Like there is a draw command buffer or draw buffer. It's fine. So we need db address, db size, and then we need storage buffer. Okay. Okay, let's run this code, see what happens. Okay, we have successfully recovered some descriptor stuff. So, and you can actually see it's sort of obvious in some sense. Let's do let's look at the swap chain. Let's look at the image. Right. Okay. So, oh wait, did I not? Yes. Cool. So, the descriptors are just a bunch of bytes, and they sort of represent the source information that you gave them, but in hardware-specific format that is sufficient for the hardware to actually use. So it can be kind of obvious how these look. For example, if you look at the buffer objects and image objects, you can see the buffer object stores an address, and it's probably a 64-bit address, and the size, and it's probably a 64-bit size, and that is it. That is all stores, right? So the buffer descriptor on NVIDIA hardware is literally just the address and size. The image has a bunch of other stuff. What's interesting here is, for example, so I'm printing the bytes in hex, and I formatted the width and height in hex, and you will see that you don't see 600, but you see 5FF, which is width minus 1. So on NVIDIA hardware, clearly the descriptor stores width -1 here, height -1 here, and then, MIP counts and formats and a bunch of other stuff in some other parts of the descriptor, right? Okay, cool. So we can recover the bytes of the descriptor from a given descriptor, but we have to know, for a buffer, we have to know not just the buffer data, but also how it's going to be used. So whether it's a storage buffer or a uniform buffer. And I don't remember, I mean, we must use uniform buffers somewhere. We maybe actually we don't. We use push constants, obviously. It doesn't look like we actually use uniform buffers. So we technically, for the buffers, it's just an address and size for us. However, for images, you have to know if it's a storage image or if it's a sampled image. Like, are you going to use read-write access to this image directly, or are you going to access it through a sampler, path, I should say. And then you have to know the format, and I'm very sure the format cannot be undefined. I mean, we can try, but something will break. Hopefully validation layers will break. Yes. Yeah, you have to specify the format like exactly as you created the image. Okay, cool. So for us to plug all of this in then, we have to do a couple more things. So the first thing that we have to do is we have to put the actual descriptor, like these bytes, into the correct place in the area that we've allocated for the frame descriptors. And we have to tell the shader to use it. So let's remove this code and let's start doing these other things. Let me briefly look at chat. And this is Wayland. I want everything as default as possible. I want minimal configuration. The compatibility with descriptor heaps should be that they are basically all DX12 capable hardware, I think, should be able to implement descriptor heaps as far as I know, which kind of tells you it's just a driver update away on desktop unless you're using old hardware. There might be some caveats. I don't know, for example, on NVIDIA if their older generation cards will even get driver updates. So you have this weird thing, I think on AMD, right? They said that RDNA 1 and 2 are like soft deprecated, like, new driver updates won't like support them. I don't know. So there's the driver situation, which is unclear, but other than that, it should be okay. Okay. Yeah, phones we don't worry about. Phones don't exist unless it's an Apple phone, which this should be implementable with Metal, like Cosmic Crisp driver, I assume. I don't know if Molten VK will ever get support for this. Okay, so okay. So now that we have code to extract the descriptor data from the resources, the next thing we need is gonna be a little, I don't know. Shaders CPP. Yeah, we had things like nicely segmented and stuff, and now we kind of don't, and it's kind of driving me a little bit nuts, because, yeah. So let's just do void star resource here. I don't feel proud of this, but I think we'll have to figure out how to work with all of this stuff, and I think it's gonna be a few tries to make that work. Why do you even have this guy actually? What does this do? Is it used? It's not used. Okay. So let's remove stuff that we don't know we'll need. What the hell we are gonna do here? Because this needs like a pointer. Yeah. All right. And then for the image view. I can't settle on one specific thing, how it should work. Let me briefly look at, so there's a bunch of buffers here. This could be just addresses. The fact that it's like the same struct is actually not that. Oh, huh. Okay. Okay, you know what? So this is gonna be a little bit sketch. Because like we're gonna play some slightly weird games here. Because like all of this is shader code, and shader code doesn't know anything about the resource code, but now we have to couple them in some way, and I don't regularly. I also want to be able to easily change the source code, our main rendering code, and have things work. And I'm worried about the long cycles where we have nothing working and then we're writing code and then 5 hours later or like a stream later, you know, we don't have anything. So I'm gonna hack things a little bit here. So I will say, okay, so there's gonna be a way to construct the descriptor info from the I don't know what happened. Is this like, okay. From the buffer struct that we have, and then from the image struct that we have, except that for the image you also need a whole bunch of other things, like basically the image view parameters. But for now, actually, let's keep it like this. And what this will do is it will just initialize everything like the same way, but also call the descriptor thing. Except that, man, this is so weird. There's so many things that just worked before, and now I have to like plumb them through somehow. So to create the descriptor info like this, to get the descriptor object, I have to actually know that the descriptor heaps are active, and I have to get a bunch of information from the global state, which I don't have in actual global variables. So that doesn't work either. Okay, I think the only thing that works actually then, and it's still not perfect in weird ways, but I think the only thing that works is we need the pointer to the resources that like the data comes from, and then we'll need to record it here, and then we'll need to use it later, and then some other stuff with formats and things like this that we'll come back to. It's pretty annoying, it makes things very non-composable, but I think I want to get something working, so I think I'm gonna hack things a little bit. And then we'll see if that was a good idea in the end. Yeah, okay. So not amazing, not proud of this code, but we need to start writing code that actually does something useful. So I think this is gonna be it for now. So we will do it like this, and then we'll do this. So what do we need? We need like image view, and this means we are still missing formats and stuff like this, but the format at least is easy. And this thing will have to be const void star, and then the image will have to store the format, because otherwise there's just nothing we can do. And there's still some details around MIPS and then swap chins. I don't remember if they have an image object, but I think at least from here we can plug things through. Create image, create image, create image. Okay. Okay. Not ideal, but that's fine. So this by itself doesn't do anything. Okay, so now when we use push descriptors, and the other thing that, right. So then the final thing that we need is when you create a program, you need to specify a whole lot of like SPIR-V binding stuff that tells the driver for a given access in the shader where to get the descriptor from. So let's start doing this, but for us to do this, we have to actually communicate somewhere that we are using descriptor heaps. And because we are doing this gradual migration, we have to do it per program object, which is kind of like pipeline state. So let's do use descriptor heaps. Let's do this, and let's actually explicitly pass this every time, because I don't want to forget this. Now you know what, I'm sure we'll get validation errors, it's fine. Let's default this to false, and then in a couple places we'll have to specify this by hand, here and here too. All right. I think it automatically converted something to a Boolean, which is typical C++ behavior. Okay, cool. Okay, so we have one program, specifically this Debugtext, where we are going to activate this thing on, and then we'll deal with the rest later. So when you do this, you are supposed to not do layouts at all. So I think all of this code, basically, most of this code becomes redundant, which is kind of funny. So all of the push constant stuff is also redundant. However, of course, we have a conundrum where we have some assertions that will trigger. Oh, maybe not. Actually, hold on. No, that's fine. Okay, so normally when you create pipeline state, you are supposed to pass it all of these beautiful layout objects that tell it how to Oh, great. Okay. They tell it how to set up the internal state. So instead, I'm very confused. Oh, got it. Okay. So instead, you're supposed to, I think you're supposed to pass it null. Oops, sorry. Old habits die hard. You're not supposed to use Alt Tab in the array. So instead, you're not supposed to pass it like a layout. And instead, you're supposed to pass it this mapping objects. So let's go wherever this and this guy. Okay, so first of all, when you create the pipeline, you're supposed to pass it a flag. And the pipeline layout must be null. And all of the resources must come from the heap. And you're supposed to tell it where to get the resources from. So let's do that. I'm not sure yet what we'll need here. We'll need like some additional state. I'm not sure what that state will have to be yet. I think it's going to be at the minimum kind of what are the resources that the pipeline uses. Yeah. I think it's going to be at the minimum this. Because when we run the code, essentially, so when we run the code, we were pre-creating all of these beautiful objects, and then the driver did some weird things behind our backs, and then the actual binding code would be very simple, because everything was hidden in the driver. Now nothing is hidden in the driver, or very little things are, very few things are. So now a lot of the code that we did, that we ran when you create the pipeline, we need some of this information to be able to actually implement, push descriptors and whatnot. So when we create the program, I think at the minimum, we will need to save which resources does the program use at which slots. And we have a helper function like gather resources, which works like this. So resource mask, gather resources, and then you give it all of the shaders, and it also writes resource types for you. So I think at the minimum we'll need this. Maybe we'll need more, I'm not sure yet. Okay, so when we create the pipeline, which should be somewhere here. So first, let's just do the compute pipeline. You give it a program, and the program now knows if it's using descriptor heaps. So if it is using descriptor heaps, you need to pass it flags. Why was this flags bit 2? Is there a create compute pipelines 2? I'm not actually familiar with this part. What is this thing? Create flags to create info? What is this monstrosity? Okay, so I'm guessing you chain this off of the pipeline creation info. And it's provided in 1.4, so we can just like use it. And then this thing has flags, and these flags should be pipeline create to descriptor heap something. There's probably way too many flags, like a dizzying number of flags. And pipeline create to use descriptor or something, descriptor heap bit. Yeah, so they probably ran out of flags like at least once, and so now they have more flags, which is hilarious. But means that we have to do this. Okay. So this indicates to the driver, hey, we are going to use the descriptor heaps. What I'm expecting now is that the validation layers will look at this and say, hey, you asked for descriptor heaps, but the source PRV code has resources that you didn't tell me where to get resource data from, and things should explode. Let's try. That is exactly what happened. Cool. Cool. So, and it even tells us, okay, out image variable. Oh, you can't see this probably. So if you forget to tell the pipeline creation code where to get the kind of descriptors for each resource from, then it will complain. So now we just have to do this. So let's look at how that works. So when we do, let's look at compute. We need compute mainly, or we need compute initially, I should say. So there's a module, there's a shader stage, create info. Stage should have a pnext. Stage is like a, oh, I see. Right. So for every stage where you specify the module, you're supposed to give it the mapping table. Cool. And the mapping table is this guy. And the way that works is, let's do this. So one problem with Vulkan structures is that they are full of these like interior pointers, which makes them more difficult to like relocate, but maybe that is not a big deal. So, okay, I think we can, I think actually this is what we need here. We don't, no, we still need resource types and resource mask because we'll need to use this. Oh, no, heap mapping is per stage. Okay. Heap mapping is per stage. Okay. Can we know this when we create a shader? I think yes. Don't think there's a reason we can't. Yeah, I think this should be fine. Okay, so what we're going to do is for every shader, we are going to compute the mapping. That will tell the driver where to get the descriptor data. And then, assuming we have computed it, which we haven't yet, we can just pass it to the driver. So if program is using descriptor heaps, then for each module, we need to pass it this heap mapping struct. And we'll get to the heap mapping to kind of what it contains in a second. Okay. So that's all done. So now when we create the shader, or I guess we call load shader, which calls parse shader, which does a whole lot of PRV parsing. Oh, but then when we parse the we can just fill the mapping like unconditionally, and then we'll just not use it. Okay, fill mapping. Shader, heap mapping, shader. Static void, or let's call it like generate heap mapping. Okay. We are getting close to getting something. Unfortunately, I suspect we are... Oh, no, we can't... This thing will have interior pointers to, like... Hold on. All right. So here's what we need to do. We need to fill these structures. The problem is, so this structure, I think this structure, so this structure has an entry for every resource. This guy references source data and source. Please not be another pointer. Source push index ext. So this guy is a union. And this guy is a source. Okay, thank God. I think this is fine. I think we just need another level of indirection or something. So basically here, we need mappings, and we have up to 32 resources, so we don't need like heap mapping, heap binding mapping. Let's call it like that. Okay. Clearly. Okay, so we need to fill the struct, and the struct has an array of these guys. And this guy for every resources tells us where to get it from. Now, what are the resources? Well, we have this function get the resources that we already used, which I think can work on one shader, maybe. Oh, we don't even need it, right. So every shader struct already has in it all of the resources that we need to access in this shader, and this is just the push constants. So we might need to have extra code here in the future for like samplers and whatnot, but I think this is good enough. Yeah, there's like 0 chance that we are 2 hours in. I think we'll get the Debugtext thing going, and this might be it for today, because this is more work than I thought it would be. Or maybe we'll see. So, but yeah, the whole thing, I don't think we can finish, that's for sure. Okay, so, but let's try to get somewhere. So heap mapping is this guy, and this guy needs a structure type. Shader descriptor set and binding mapping info ext. Oof. And then for every mapping, it will have an entry here. So basically then okay. Okay. So then we need an array of these guys, and these guys are that thing. And let me just copy this whole thing, paste it in my source code so that I don't have to like switch between stuff. And then I will talk about what the plan actually is. Okay, so the plan for push descriptors is to use what's known as push index. What push index does is it allows you to say, okay, the way you access this descriptor is you take an integer from push constants essentially, or push data it's called, but it's the same thing as push constants. So from an array of like untyped just binary data that the shader gets from like with each invocation, take this index and then perform a very simple algebraic transformation on it. Like you add, you multiply by stride, you add an offset, and this is the offset in your descriptor. This is basically what we need. I keep forgetting things. To create a shader, we'll need the resource size. Let's hack the resource size for a little bit and then we'll see. So this is the thing we are going to use the most because this can support our entire push descriptor setup. The plan is push descriptor tells us we need 7 descriptors. We are going to add 7 descriptors to this region of per frame descriptor storage that we have allocated. And then to the shader, we'll just specify the index. And then the shader will read that index and then do this transformation to get the actual offset and that of each descriptor, and that is it. So really, the only thing that we need is push index. For samplers, I think we will have to use another thing which is called constant offset, but everything else we just don't need. So we'll need, which is good because this means that the thing that we are going to be filling is not all of these structures, and it's just this thing, and this we don't need right now. We might need it later. So that simplifies the stuff that we are going to be doing a little bit. So let's just copy some code here. So in each shader, we just go over all of the resources. We say, hey, will we need these resources? Yes. Okay, cool. There's one minor caveat with gaps, but that is fine. So then we need to fill the mapping. So we have this beautiful array which we will allocate an entry in, and then let's see. So S type, and I hope we don't have to chain any more like pointers to this. And binding mapping. Why do we have? Okay, whatever. We have some local enums. It doesn't matter. So descriptor set is 0. Which is implied. First binding. This is a little bit similar to filling the descriptor, the information for the descriptor set. It's just that we are not using descriptor set and we have a custom like layout. So first binding is the binding number I. And we just have one binding. Right now we don't support arrays yet in this code. We will need to, but probably not today. So then there's this thing called resource mask, which I think you can actually don't know what this is. So we'll let's just look at the resource mask. Okay, yeah. So for the resource mask, I think this is for arrays or for some other like complex stuff like this, where you have like mixed binding types within a given like array. I don't think we need this. So source is going to be push data, mapping source push data. This doesn't work because I was planning to use push constant size as an offset and we don't have push constant size here. That is fine. Okay, we are going to be hacking a lot of stuff right now just to get things going, and then we will consider our life choices separately. So source data push index is the thing that we will need to actually fill, and then everything else we don't need right now. Okay. So heap offset. Let's just ignore this. So push offset is the main thing we can't fill. Is filled later when we know push data size, which is not great. But I could move this later. Okay, that's fine. Actually, why? Oh yes, that's fine. Okay, so heap index, and then we also don't know the descriptor size. Okay, so it doesn't quite work. But again, I just want to have something working, and then we'll deal with this later. These are not arrays. Oh, okay. And we don't know that, right, okay. So basically the big problem is this. There's two things we need to know. One is the descriptor size. When we tell the shader where to get the data from, it takes the constant from the push data, but then it multiplies it by the size that is baked into the shader, and the size should be the descriptor size. We don't really have this constant here. We have it like elsewhere where we fetched it, right? But let me just hard code it. I think it was 32. This is the max buffer image disk size on it. Oh, 64, right? Hold on. No, it was 16 and 32. Okay. So this is not great, but we will come back to this. And the other thing that we didn't tell the driver correctly here is this push offset. So push offset tells you which offset in the push constants blob do you read to then do all of this math on to get you the resource data from the descriptor heap. So you can put it at 0, but this means that we have to go into the shader like this, and it has push constants, and it has this text data. And so here you have to do an additional like push offset. I was hoping to be able to put it after the push constants. So after this guy. But to put it after this guy, we need to know the size, and we don't know the size here because it's specified like when we bundle all of the shaders into a program object. Now, I guess this is not as big of an obstacle as it seems, because there's no need to pre-generate this. So, okay. So I guess let's just do all of the stuff on the fly, or more of the stuff on the fly, because it's going to be easier to wrangle, I think. Yeah, and then we can pass, instead of the boolean. Oh, okay. I kind of like this plan. Okay, so instead of putting this inside the shader, we'll just have a helper function here that generates the mapping. And into the thing you ask it to generate to. Or I guess it could be. Oh yeah, this is actually almost the same as update template. Yeah, okay, so I think it's in the right place. It's just, so this is gonna go here, and then this is gonna go here, and then in fact we can just return vkShader descriptors set and binding map info ext. Okay. Hopefully this is making some amount of sense. Okay, so this is actually super simple. Now, the good thing about this is that we can actually pass through data that we didn't have like there. And the data that we lack is push constant size. And the other data that we lack is descriptor size. Now the thing is, we can actually, instead of passing a boolean that tells us whether we use descriptors, we just can pass descriptor size and use like it's never zero, etc. Okay, so this actually is fine. So okay, so then again, the plan is this. We have the push constant block, and after it, we have the integer, which is this push index. And then this tells the driver, read the integer from this offset, multiply it by descriptor size. If it's an array, then multiply the entry in the array, but it's never an array, it doesn't matter. And then you get the offset into the heap that then you can use. Which means that if the thing we write into the push constants right after our actual block is the offset into the frame descriptor set, frame descriptor like data, then we should have the correct and full solution. Now the only thing is we need to now use this, pass this to like the driver where it creates, when it creates the structures. But I think this will work actually. So, okay, this is why I didn't, this is why I wanted to cache it in the shader, because the graphics pipeline gets really annoying. But let's actually punt on this for a little bit and just do the compute. If this works, that is gonna be crazy. Okay. Okay. All right, and then instead of use descriptor heaps, we'll have descriptor size only used for descriptor heaps. And then here we can just replace them, and you can keep the boolean. I like not having redundant state, so I will do it like this. But you know, you can certainly keep the boolean if you are doing this in the engine that has easy access to, like, depending on how you have things wired together in your engine. Some of the things that we are doing right now may seem like, oh, this is stupid, you know, it should be way easier because blah, blah, blah. But obviously this code was started in 2018. Descriptor heaps were not on the horizon. Oh, and I forgot, before I forget, when we create program here, resource descriptor size. Okay, now we can do shaders for size team. One. Okay. Okay. Okay, so now we segfaulted. I don't know if it's good or bad. We segfaulted somewhere without any validation issues. Cool. So let me think about this. The thing we didn't do yet is we didn't change the code on the C++ side. So we are now passing a bunch of extra data to the driver when we create the compute pipeline. And this data tells the driver how to like generate the shader microcode so that when the shader microcode runs, it actually gets access to the right descriptors from the heap. We haven't written that code, so a natural conclusion or a natural possibility would be, hey, the code should crash at runtime, or the GPU should like crash at runtime, something bad should happen. This actually didn't happen. What happened instead was we got a crash, what looks like roughly when the driver creates the shaders. So that's interesting, and we didn't get any validation errors. Okay, so that is concerning. If I fix this right now, then we still will have a problem, which is that when we run the rendering code, we haven't actually used all of the new APIs. And so the actual rendering results, and we'll have something bad happen. Because we haven't filled the descriptors at runtime. We have just filled the PRV stuff that is required for the shader to read the descriptor data if it's there, but it's not there. I want to write the sketch of this code first, even though right now we are not getting to this. We are crashing, you can't see this maybe, but we are segfaulting like right after the shaders have been loaded. So it's probably program creation or pipeline creation. However, if I fix this and I run this, then we for sure are going to get a GPU side issue. And GPU side issues are even more annoying to debug. So with that in mind, let's do this. I don't fully understand. Oh, is this because the search? Okay, yes. So let me change this here, I guess, just so that we have something kind of working. Like I want to have code that pretends to be working, even if I don't know if it's working or not. Just so that we don't run into bad surprises later. So remember, these two calls are outlawed in the new descriptor set regime. So if the program was compiled with descriptor sets, we can't, with descriptor heaps, sorry, I keep saying the wrong word. We can't use these calls. We have to do something else. For push constants, it's very, very simple. So if we have a descriptor size in the program, then what we have to do instead is we have to use this push data. And it's the same as push constants, it's just more typing. Like you have to do this data info, and then you have size and data, and then you have push data X. So push data info size constants, push data info p data, p data constants, size of constants. I don't know why it's upset. And then like this. So that is it here. Why is it upset? Oh, because it's data dot p data and data dot address. This example is out of date. The official feature proposal has code that doesn't compile, so that's cool. Okay, so that part is very easy. The part that's more difficult is the actual descriptor stuff, because this is when we actually have to get the descriptor and then put it into memory in the right place and all of that fun stuff. So let's just write some code here. Again, I don't know if it's going to be correct or not. It might be like broken in various ways, but I just want to have code that pretends that like it's working. And then we will have to figure out why we are even crashing. So what we have to do here is this. It's kind of sort of simple. Kind of want to have a resource count and not resource mask. No, actually, maybe that's fine. Okay. So what we want to do is conceptually simple. So we want to iterate through all of the resources that are used by our program. There is a little thing with gaps. Oh, never mind. We have push descriptor count. Okay, all good actually. So then we want to assert that we have space in the descriptor buffer. What does it mean to have space? This means that the offset plus however much we need to write is less than or equal to frame desk offset end. That's it. So then we want to write the descriptors to the buffers, and then we want to advance the descriptor offset by the program push descriptor count. So then here is where we will write the descriptor data to the actual memory. And then remember, we just did this push index setup where we told the driver right after our push constants, read the index, use the index to reference the data inside the descriptor set. Well, we need to write that index there. So for that, I think we should be able to, and if not, then there's going to be a problem. But I think we should be able to do another push data, sort of redundantly. You could fuse the two calls together, but we'd have to restructure our code to be able to do this, and I don't want to do this. So I hope what you can do is you can just say, descriptor offset, and the other thing is what you need. Oh no, you don't need offset in bytes. You need literally the same integer. So you need literally the program, not the program, frame desk descriptor offset, because this is the index of the descriptor, and we already have multiplication by the stride inside the SPRV mapping. So this is all it should be. And then it should be a uint32t. If it's not, something weird will happen. So let's assert that size of this guy is 4. Because if it's not a 30-bit integer, then actually, let's just do this. Offset, offset, push data, and then that's it. And then the only thing we have to do is we have to fill the descriptors. Now we just did this get descriptor calls that required you to get so much more data than we have available. The way we are gonna work around this issue, sort of, is so I had this void pointer stashed, and so we're just gonna assume basically let's just assert program resource types is vk descriptor type. I think it's like storage image. Let's not even support sampled images. And then let's just then assert that the resource pointer is not null. And then let's assume it was an image object. And then let's use the get descriptor call. And to, yeah, this is why I'm saying there's no way we can actually finish all of this, because there is so many like shortcuts that we are doing right now. There's so much more to implement. So we need the device, which we don't need, by the way, so I guess we'll put that in the frame descriptors struct. The image object provides you the image and the format. We don't have the MIP level, let's assume it's 0. We don't have the level count. I don't even know if you can specify, let's specify 1 for now, but descriptor, we don't quite have the descriptor size. Okay. So we will put the descriptor size in the frame descriptor too. And then the other thing we'll need in the frame descriptor is we'll need a pointer, because we will need to mem copy the descriptor that we just got from the driver to the actual heap where it will be visible to the application. Descriptor heap plus frame desk descriptor offset plus, and here we are kind of doing the same calculation that the driver is going to be doing for us in this PRV code, plus I times frame desk descriptor size, and then descriptor, and then frame desk descriptor size. We could also just directly get descriptor into the target memory. There might be some performance issues because of this, so we are not going to do that. Okay, and then here we'll need device. We'll need descriptor size, and we'll need the key device address descriptor heap. And ideally, you can cache the descriptors somewhere. there's so many things to figure out. So I don't wanna do too many things. We're already doing too many things at once, so I don't want to do too many, like more than too many things at once. Wait, this is not right. This should be not the device address. This should be the actual like host pointer. And here it's a byte offset. So this should be the data, I think, pointer. Okay, and then descriptor size is resource descriptor size. Okay. All right. I have no idea if any of this code works, because remember, we are crashing before this code runs. So I just wanted to have some code that like that runs, and then we can actually debug the actual CPU side issue, and then maybe once we debug this, something will render, or maybe it won't. Okay. Let me quickly scan through this. Yes, it's Vim editing style. So you can pass buffers as a device address. The reason why we are not doing that is because there is a bunch of other code that we'll have to rework, right? The other thing is, if you're passing the buffers, if you're using device address, my recollection is basically you would have to assume storage buffers, not uniform buffers. There is potential performance issues with this on some NVIDIA hardware, in the sense that uniform buffers are somewhat faster in certain cases on some hardware. So it's not completely free if your access is uniform data style. So if you just need an address to just get like a few constants, and these are the same constants, then I'd be thinking about, is performance gonna regress on NVIDIA or not? If you're using a storage buffer anyway, then as far as I know, there's no cost. There are weird interactions with robustness. If you have a storage buffer and you're indexing it outside of the bounds of the buffer, what happens? Here, we are still passing the offsets and sizes. Remember, the descriptor had the size, which means that the hardware will, in some cases at least, depending on feature setup and stuff, use that size to do bounds checking and safely read outside of bounds of the buffer. So this is the capability that you're losing when you use buffer device address. And also there might be tooling implications. It's like, oh, this tool can't reinterpret the device address and stuff like this. But yes, an alternative, so we just did a bunch of things. Who knows if they work? It's just one shader, I think if this works, then we are close in the sense that in Vulkan's typical style, the delta between rendering a triangle and a full mesh is not that large. And all of the stuff that we've set up is like 90%, I think. We didn't do buffer handling, or we didn't do samplers. If samplers weren't involved, we would be almost done, except that the code crashes. Samplers require a little different setup, so but where was I going with this? I forget. Oh, right. The other thing that we could have done is a full bindless setup, meaning we have no bindings in the shader code at all. We just have push data. We have indices there that inside we pass the resource. How does that even? Because you have to, somebody has to multiply by the resource size. And I'm not really sure where this would happen. So I haven't really looked, but there is a GLSL extension that adds an ability for shaders to directly index into resource heaps. I'm not sure if they have a way to specify these strides like somehow. But there is the world in which your push data is just 10 indices to 10 different buffers and textures. And then inside your shader, you manually index them. That is fine. I don't even want to go there personally, because I like the explicitness in the source code of the shader of being, this is the buffer of this type. I'm indexing it with this type, you know. But you can do this, and as far as I know, other than the storage buffer stuff, it should be fine. So there's complicated and general interactions between things that we are doing right now in performance. It would take like a separate stream to go into this. Because there will be a second stream. Maybe we'll talk about this next time. But anyway, okay. So let me try to debug this code, because we are crashing somewhere now when we create the shaders. I'm assuming we are crashing in the driver. There is zero output from the validation layers. Oh no, this is actually better. We are crashing inside the validation layers when trying to presumably write the error or something. Or maybe not. Okay, this is less bad than I thought. Okay, so create compute pipelines is crashing because it's going to a bunch of pnext stuff, and at some point it goes into pnext and then like dies. So it's trying to go through pnext of the set. Did we not initialize? Oh my god, of course. When I moved, okay, that is my fault. That is my fault and nobody else's. See, I'm glad that we've written all of the other code that we have written, because, okay, things were just not zero initialized. That's fine, you know, C++, cool. Okay. So now I don't know what will happen. So now, there was a trivial problem in the validation layers where it was crashing, trying to go through a bunch of pointers that weren't initialized. So now, unless we have an obvious bug here in the code that is visible to the validation layers, what will happen is we will compile shader microcode, and then we will attempt to actually run it on the GPU with whatever descriptor stuff we have like passed to the GPU right now in this code that I just wrote. If that doesn't work, the GPU crashes. So when the GPU crashes, I think my expectation is the stream will stay alive, but there might be a gap of like a second or so in audio and video because let's see what happens. Oh no, thank God, we have a validation error. We have an actual validation error. Okay, so we have an image and it's telling us we are using storage class. Huh? What? Okay, that is a thing I did not expect. Okay, so push data is used to be the storage class uniform constant, but it must be storage class uniform. I don't even know what these words mean. I roughly know they refer to some spear v like. So this is the out image. So it is saying the mapped resource must be a variable with a structure type decorated with block in the uniform storage class. Oh, push, not, sorry, hold on. Push data. I used push data. I should have used push index. I'm surprised. I'm feeling push index. Okay, push data is a different thing. Push data is, I want to create like a virtual uniform buffer around like data inside the descriptor buffer. It's similar to the ext inline uniform block. This should have been push. We should have been like this: source heap with push index. Okay. Right. Okay. Attempt number 5 or whatever. Okay. Now our assertion has failed, because the push descriptor count is not equal to push descriptors. So this is an assertion on our side. Push descriptors is 1. Are we not filling it now? Push descriptor count. Who's filling this? Oh, yes. We have lost the code that fills this. We need this code basically. Oops. Hold on. All right. We need, let's do this again. So this is we have this thing called resource mask that tracks which resources are used inside the push like blob. We don't have a count for this. This is literally just give the like sort of last, like the location of the last set of the most significant set bit plus 1. But you know, the C++ doesn't have this until C++ 20, blah blah blah, whatever. Let's try to run this. Okay. Okay, yes. So now we are finally getting to the meat of the thing that we spent like time agonizing about in the beginning of the stream. Okay. So when I pass descriptors, I now have to make sure that each descriptor info has the resources that the thing comes from. And for swap chain, it's particularly strange because I'm not even creating the image objects. And so what I have to do is I have to do fake swap chain image, which I have to fill myself, because I don't have like an image object, because I didn't create it, because it's a swap chain. But swap chain is the only thing that's uniquely special like this. So, and the format is separate and stuff like this. So I'm hoping it doesn't matter actually. And then we can be generous. We aren't going to be needing the image views, but let's specify them anyway. And then there's the memory object handle or whatever. Yeah. Okay. So then in theory, I can, because of the plumbing that I did with descriptor info, that's a little hacky. In theory, I can just say, okay, give me the actual image object instead of the underlying data, and then things would still work. Let's see if the GPU crashes now. Okay, the good news is the GPU didn't crash. The bad news is we don't have the text rendering. This is about the worst possible situation, because who knows why nothing is rendering, right? It could, so now the bug could literally be anywhere. Well, at least the code doesn't crash the GPU, I suppose, so that's cool. One thing I'm curious about is, so if we now go and say, oh, actually, I don't want to use the descriptor heap for this draw call, do things still work, or did we break something more fundamental earlier somewhere? Okay, so that's actually great. Now that we know the original path still works. The code doesn't work. That is sad. There is multiple possible explanations. So, for example, it could be that push data is actually unsafe to call twice, but I think it is safe. Did I do the offset? Oh, I didn't do the offset. This is why. Okay. Why did nobody stop me? Maybe somebody did stop me. Okay. So so remember this integer that is specifying the offset to the descriptor data is after the push constants. So we have to tell the driver to update the push data after the offset, or like at the offset, which should be inside. Yeah, so like right after push constants, we have the descriptor offset. Okay, now maybe something exciting will happen. Oh my god, people. We have successfully persevered and rendered the freaking text through a shader that heroically accepts the image object. It is funny that nothing exploded in catastrophic ways, because when the offset was 0, the behavior would be like strange, because like nobody would ever be writing to the push data like with the offset that the shader is reading from. So it's kind of garbage index that goes into who the hell knows inside the descriptor heap and then does something unspeakable. It's a miracle the GPU didn't crash. But now we are using the actual resource heap successfully for the one draw call. Oh my god. Okay. I think we should celebrate this occasion by committing this code in whatever state it's in right now, even though it's terrible, because now I'm scared, you know, I change something else breaks, etc. It wasn't broken before, bad things happen. The if-def situation is annoying. So basically what should happen is I should have if-defs around, for example, this whole thing, right? But maybe that's fine. Let me put if-defs or ifs so that we actually, so that at least we attempted to make the code compile. If you don't have the extension. And again, we only do this because what if you compile with an older headers that don't support this yet? If you update to Vulkan SDK, it doesn't matter if your hardware has support for it or not, right? You can compile the code obviously just fine. Where else? I guess I could look at the diff. All of this PRV stuff that we were just doing. So this part is fine. This part is fine. All of these objects are now null. We should not be destroying them because we aren't even creating them. I will fix this in a second. Is the if-def battle just lost? Should I not even bother? Because there's so many of these. Because it's like here and like here and that whole thing. The only way to know is to like actually try to build it. I don't want to waste time on that right now though, so. Okay, and let me, so the nice thing about all of this pain that we went through is that we have all of these older objects. So it used to be that our program object has all of these like objects allocated inside the driver that had all of this sacred knowledge about what to do. We don't need that anymore. Like, we only need this when descriptor size is 0, as in the descriptor heap is not used. So that's nice because once this code gets eventually removed, the totality of the like the result in total is simpler. Right now the result in total is like more complicated because okay. All right, I'm relieved we didn't run into crazy GPU sites or like just bugs that would be impossible to trace or debug, because I was not looking forward to that part in particular. Of course, we only converted one shader. one shader, which is not a lot of shaders. Okay. Oh, this code will not compile. Okay, things are relatively in shape, I would say. This code will not compile. I'm not confident that it compiles. After all these if defs, there is some stuff with buffered rest to clean up, etc. But this is a good start, at least. We fixed push descriptor count. This code will not compile. What is this? Oh, this is the graphics pipeline. Right, and we haven't plumbed this code through in the graphics pipeline creation code, which is actually trivial to do. Is just that it requires like arrays of things. It requires arrays of things, and arrays of things are always annoying to. Should I just do this right now? Okay. What's the total shader count? It's like 3, 4. Because yeah, you have to chain essentially. Unfortunately, this whole mapping thing is specified per shader stage, so it's not like per. Like you can't basically have this array, or can you? Because it's interesting. I'm specifying. You can. There's no reason why you can't. We have to tweak. When we say generate heap mapping, we tell it to generate the heap mapping from the specific shader. But the mappings in our code are parallel, or yeah, parallel across shader stages, meaning if a resource is index 5 in a given shader stage, it's also index 5 in any other shader stage or unused. So really, the only thing we even use from this guy, how do we not? We are cutting a corner. We don't use the resource type, but that's fine. Okay, so really, okay, so this is actually great. So I can do this in compute with no issues. So really, what we need is, here's the resource mask. We don't need the shader. Here's the resource mask. Here's resource types. Just generate me mapping that like maps this through the push setup that we have. It doesn't depend on the shader stage at all, which means that when we have a compute shader, we can get this data just from a single stage. Why not? Const, right. And then when we have a pipeline, like a graphics pipeline, it's actually still simple because we can. Hold on. Is there? Do we already have? I think we already have this in the program, maybe. Yeah, program already aggregates this. So actually generate heap mapping could have taken a program, right? But because we wrote this earlier, okay. So actually you just need a program, but let's just leave the code like this. It's a little bit more usable this way. Okay, so this is great because now we, what do we do with this? We generate the mapping. Then if we need this, then here we just chain the same thing to every shader stage, and it should still work. Okay. Okay, we can't test this yet because we haven't, like the only thing that we support right now is a single compute shader, but that's fine. Okay, I think this is good. Let me commit this because I want to have a good state, and then, okay, we are almost at 3 hours. All right. Yes, okay. Indeed, initial descriptor heap support. If descriptor heap is supported, we now use it to render debug text, and only debug text. Some infrastructure is not fully fleshed out. Instead of using traditional descriptors. And I don't know what to. Some future refactoring is needed in addition to actually converting the rest of the code. All buffers now have buffer, and this is, and the descriptor info. So the biggest weird thing that we still haven't figured out is this whole connection between the descriptor info and the buffer objects. If you have an image view for like a different, for like a single MIP level, how do you specify this? So all of this is a little annoying. And then also we ask the driver to give us the descriptor for every resource every time we bind it. You can cache it. If you cache it for images, you have to cache essentially 2 descriptors. One is for storage, one is for sampled usage. All of this is, oh, and then per MIP level, right? So what if I want a descriptor to point to a specific MIP level? So all of this is like not great. It's kind of similar to ImageViews. Yes, there is no ImageView object anymore. But if you don't want the driver to do expensive work every time you want to procure a descriptor, you have to have a descriptor object. Is there a difference between an image view and like a 64-byte like thing that you manage yourself? I don't know. Not a big difference to me. Okay, so I'm yeah, the removal of image views is I'm sure well-intentioned. For us, it's definitely not working out. Everything else is fine. Everything else is fine. Okay, let me see. I don't really know what you mean by access chains. Descriptor heaps are not access chains. Descriptor heaps are just heaps. Okay. So let me look at what happens before the debug text, just to see what it would take. So this previous one is intense, kinda. So it has samplers. Does it have samplers? Is a sampler here just for show? Because I thought it's like a sampler with nearest. What even is this shader? Is this like final composite? Yeah. Why are these samplers? Oh, we are using texture. Unapologetically. Huh. I thought at some point I converted all of these things to image fetch, but I guess that didn't happen. I'm now wondering why. Because text will fetch. I guess text will fetch still needs a sampler. Just kind of strange. Why does text will fetch need a sampler? There's nothing to filter. The level of detail is explicit. There is no addressing math because you just specify the pixel or like the textile coordinate. Huh. That is strange. What happens if I pass like a null handle? I think this might be a limitation in our C++ code, because we assume do we? This is actually a little strange. Hold on. Oops. Final comp. I don't know, like shadow data. Oh, right. Hold on. It is using texture right now, not textile fetch. Hold on. I'm not even looking at the right thing. Let me try to change final comp here to do textile fetch, shadow image, pos 0, or whatever the arguments are. Okay, so now, do we really need the sampler? The descriptor type is still combined image sampler. Yeah, okay, so what is it in the shadow image? So it's binding for descriptor set 0. It's like uniform constant or whatever nonsense. Wait. Yeah, where's the actual type? 160. Sampled image. So it is type sampled image, but it's not a combined. Or are these the same? GL or SpearV is like so weird about these things. I always forget. But I think it's because when we have a sampled image, we assume it's a combined image sampler, because there is no way for us to tell the difference. And that is actually quite annoying. Although I'm actually kind of confused. I guess maybe you can't not. You have to have the sampler. It's just so weird that you have to have the sampler. I'm a little bit blanking on this, I'm not sure. So what I was hoping we could try to do is to do one more draw call. But unfortunately, everything that uses samplers requires more setup. And that setup is like, it's not more work that we have already done, but it is more work than 5 minutes, and it's already 3 hours. So that sucks. And I'm not even confident I could do the rest of the thing in an hour, and I do not have more than an hour. I have a little bit under an hour left. Okay. And the problem with converting everything else is that, remember I was talking that the bindings like disturb each other, and so you'd have to rebind the buffer like multiple, not the buffer, the heaps multiple times. So that is bad. We could convert calling, but even calling needs samplers because it reads from the compute, or from like the depth pyramid, which needs a sampler. So that's unfortunate. I can like convert the shader to use image load, and that would convert these guys to just be regular images. And but that proves nothing actually, because this shader is interesting. It doesn't do more. It's just a bunch of reads from an image and writes to an image. It doesn't do more than the Debugtext shader. So in that sense, the Debugtext shader was like a perfect, simple representation. Okay, you know what? I think it might be rational to just call it here for today. Because to recap, we don't have samplers. It's so tempting to just hook up combined samplers, even if it's like in a hacky way. Even if it is... It is very tempting to hack in samplers. I don't even think it's that difficult, especially once I split them. Hold on. So I can split in the sampler object, split off a sampler object. So, oh, by the way, so these are combined image sampler objects right now. I think in general, the combined image samplers are going out of favor in Vulkan. They are, if you are not using descriptor heaps, they are important for NVIDIA hardware and maybe some other hardware, but in like a minor way. The deal is basically on NVIDIA hardware, is especially if you use bindless, like the descriptors are just integers and they split the indices so that the combined image sampler is like 20 bits of image index and 12 bits of sampler index. And if you have a separate one and it's like 2 integers, so it's like there's marginal, you know, efficiency loss, but it's not super important. But despite this, the descriptor heaps extension does support combined image sampler objects. It does it in a slightly funky way because it has the same 12-bit split that I was talking about. I'm actually, but so I'm actually I'm so confused now. How do I tell the combined? So let's say instead of this, I think I am so confused. Hold on. So in this code, I have a separate sampler object and I have a texture 2D array. Oh, is it texture 2D versus sampler 2D? Yes. Okay, so if I have a texture 2D object in GLSL, what can I do with it? Can I do anything? Can I do textile fetch? I cannot do textile fetch. Oh, only if I have GLEXT samplerless texture functions. Okay, I wasn't just confused randomly. I was confused because the restriction makes 0 sense. And 8 years ago, there was an extension added. 8 years ago. This is before Vulkan, presumably, in the sense that it's probably a GL extension. Okay. So this allows you to use textile fetch directly on the texture 2D object. Okay. Not having this makes 0 sense. Okay, so what happens if I know I said we won't change the shaders, but you know, sometimes you have to. Okay, so now that I've done this, do I still have a problem where I'm using a combined image sampler? I bet I do. Oh no, it's probably not sampled image now, it's probably image with sampled bit on it. SpearV is weird, people. Okay. So if I just have the image view now, will things work? Okay, people, we are converting the second draw call just to prove that this works. This should have used textile fetch anyway. There's no reason to use like samplers if you're not like filtering an image, and it actually is faster on some hardware to use textile fetch in these configurations. So these guys are now texture 2Ds. And that means that in the source code, we don't need samplers. By the way, the nice thing about, so if I wasn't using, right now I'm working with still, so this part of the code is still not using descriptor heaps. When I'm changing these descriptor related things, the validation layers catch my mistakes. This is because the validation layers have information about the things that I'm using and how I'm using that. This is because this information is direct. I'm using an abstraction over descriptors that is explicit but not low level. It is explicit about which descriptors you're using, where and how and why. But it is not low level in the sense that it doesn't map anywhere close to what the driver actually does. The thing we switch to descriptor heaps, they are low level but not explicit. They are low level in the sense that this code maps very close to what the hardware actually does. There's still some differences. Maybe your hardware doesn't have descriptor heaps as a dedicated like hardware binding thing. And so then what the bind resource heap does is it reserves some address somewhere for where the pointer to the data will leave, just as like an address. And then the shader just reads from that address. But it's still very direct. It's like very low level. It's almost the same thing that happens to hardware. However, it is not explicit anymore. Because I filled some like tables for the driver to know what to do in the shader, but A, I didn't have to do this. B, I don't know, the validation layers could, in theory, look at, it's like the descriptors that I'm filling in the memory, they are GPU specific bytes. The validation layers don't really know that I have put these bytes there. I just mem copied them, right? So in theory, it's possible for the validation layers to somehow validate all of this. I don't know how they're going to do this, but I've been told the descriptor heaps are the future, so it's like their problem, not mine, which is great. Where I'm going with this is that I think it's actually, if you have to do shader reorganization, right now it's actually safer to do this with descriptor heaps off. And then, you know, the code hopefully still works when descriptor heaps on. So it's a little bit of a weird like situation, right, where you are like we wrote code that is more direct, but the code is now more dangerous and we have fewer tools to help us work with that code. So that is like an interesting consequence of all of this. Okay. So I think what I can do now is I can first switch to our new like mode for how to initialize descriptor info. And now I think I can literally just switch the one more draw call to descriptor heaps by moving it after I have bound the descriptor heaps. If I just run this right now, weird things would happen because this code is not using descriptor heaps. So these bindings are invalidated. Does it actually invalidate something in hardware? I don't know. It's hard to tell. But we just have this pipeline, which is actually a compute pipeline. So we can just pass a descriptor size, and that automatically enables everything. And and that's actually good to do because it forces us to fix some hacks. So this is actually just an assertion. Because we propagate the resource type through, things will still work if it's a sampled image. So that still is fine. Well, okay. Interesting. Okay. So clearly we have more problems to solve. This is interesting. Did I cut more corners somewhere? I didn't think so. So this just passes all of the data. This should get sampled image as a descriptor, as a resource type. It should generate the correct descriptor. It should like mem copy it to the right place. The difference between this code and the shader and the previous shader is that this has way more, it's a second draw call or dispatch or whatever, and it also has like 5 descriptors. So on one hand, it's logical that there is some difference. On the other hand, I wonder if this also forces us to be actually correct with all of these sizes of push data. Let me see, shape data. Yeah, it's aligned to 4. This has padding. It's quite unlikely that this is a problem. Yeah. And we do know this extension works because we checked the code before. So let me do some spot checks. I think it's going to be the final thing that we do if it works. And then if it doesn't work, then it's going to be the final thing that we don't do. The debug text still works, which is interesting. So it's like this specific thing is now broken. Did I... Oh, the push constant stages is not initialized, I bet. So this if is just wrong, basically. Yeah. Let me just delete this. I don't fully know. We don't really need this thing here. Yeah, okay. I think this was the problem. No. Is it a problem that push constant stages is not like... No, this was only relevant for the old path. Final program gets resource descriptor size. Oh, this thing still says false, by the way, which is not great. We could like check the... Let's check what the hell is actually like going on inside push descriptors. So like here, right? Push descriptors. Push descriptor resource type. So yeah, this looks correct. So we have the sampled image like 4 times, and then this guy is the output image, so that's a storage image, and this is our final pass, which does let's also say push constant size. Uh, 112 bytes. That might be true. This is 64, so this is 4, 5, 6, 7. Yes. So this is 128, 7, 16 byte like lanes or whatever you want to call them. Interesting. Yeah, so this is very interesting because this shader isn't even complicated. It's just like, you know, once we get to ray tracing and stuff, things are going to be wild, maybe or maybe not. But this one is the same. It's the Debugtext doesn't use storage image. This guy does. Other than that, this is not interesting in any particular way. And what happens if I just ask it to store like some ugly color? Okay, ugly color works. It also cuts out... What do we actually see? This is so strange because it's like 2 frames overlaid, right? Wow. Huh, what? Interesting. So this is as if the shader like right doesn't even work, because I think what we see is sort of all of the rights combined. Wow. Which is very strange, because so it's like this is what you would get if you, for example, discarded the pixels. But this shader doesn't discard the pixels ever. It just reads a bunch of RGB data and just writes it. So I bet like, okay, so what if we do output color equals like depth or whatever. Interesting. So okay, so white, well, white is a bad color because, no, actually, okay. Yeah, so when you output a single color, things are fine. We are still writing the descriptors, by the way, because they're still bound like in the shader, like they're part of SPIR-V metadata. The driver optimizer presumably strips all of this stuff out, but the thing still works. Okay. But the second you use any... Oh, this could also happen if the sampled images are aliased in a weird way. Let's say the driver, let's say the mapping that we have filled is broken, and let's say actually the index is ignored. I think I forgot to shift each subsequent resource maybe. by an offset, yes. So this is funny. All of the resources would reference the first one. And so they would read the previous contents of the swap chain, which is like whatever it was in the previous frame, and then combine it in like weird ways and then write it back. Okay. So whenever the shader does this beautiful math, what actually should happen is that every so the push constant has the offset of the entire descriptor block, but every next descriptor there should be offset. So this heap offset, I believe, should be I times descriptor size. Heap offset is like a constant offset. Okay. Perfect. I'm glad, well, in this case, there was nothing to blow up because they would just read a valid descriptor. It would be just different from the descriptors there. Okay, great. I don't think we can do one more. I think one more would be pushing it. Let me check what's before it. Is it like ray tracing? The blurring can work because it has the same like stupid. Let's fix it regardless because okay. So this is actually nice in how now gradual it is in certain places. Like, you know, you just find things that basically some subset of shaders can be easily converted to the new path now because even the bare minimum like infrastructure that we have set up is sufficient. And so the process is quite simple. You just remove the samplers and oh, not image 2D, texture 2D. Yeah. And then you are done. Or rather, you remove it, check that it works before descriptor sets, and then like switch to descriptor sets. The only thing is I have to do this for the entire block. So let me see. So shadow checkerboard, what is it? Is this shadow fill or something? Yeah, so these guys should be using texture 2D. I didn't know about this extension, but I'm glad it exists. Okay, so that is it here. So shadow filled should be ready, and then the previous thing is the ray tracer. Oh, this needs a texture sampler. Why does it? Oh, the actual ray tracing thing is complex because in addition to what does this do? This does shadow, right? The shadow casting code supports textures with alpha. Hold on. Shadow, not shadow fill. Okay. Shadow. Okay. So this thing is kind of funky. I'm actually not quite sure. So this is the same problem as before. This also needs buffers, which we haven't plugged in. I guess, yeah, this one needs filtering. Yeah, so when we do shadow casting for transparent objects, we need to sample. So this one is tricky because it's a full bindless. This is one of the difficult shaders. It uses acceleration structure to trace rays. It uses buffers to get a bunch of stuff. and it uses an array of texture objects, and it uses a sampler. And so to make this work, we'll have to fix this, which is easy, fix buffers and acceleration structures and such, which is maybe easy, but who knows, maybe not, I'm not sure. And then you will need to actually implement support for samplers, which again, none of this is like super hard now, but I'm getting tired. So I think this is good to call it. Let me just for consistency. Wow, this is an impressive array of extensions. Convert this. So this should be texture fetch. This should be ivec2 plus 0. And here, this guy should just be that. And we can even drop these buffer annotations from it, but unfortunately, this doesn't let us run the code yet because of the whole sampler stuff. And so more cleanup would be necessary to be able. Texel fetch, not texture fetch. Or more work, I should say, yeah, would be necessary to have like everything work. We can use the descriptor heaps for parts of the ray tracing pipeline now, but not the entire pipeline. And so we kind of can't move the thing up. And if we actually had enough infrastructure to move it up, then we probably could have done the rest in like 15 minutes, because this is the actually difficult shader, because it needs samplers and acceleration structures and buffers and whatnot. Okay, I think this is a good time to call it. Good point, I should say, to call it. Okay. Using NDA terminology on stream would not be a good idea. I don't think texel fetch clamps, right? I mean, does it? Let's see. I mean, this doesn't say. The extension that we have switched to probably says if it clamps. It would be surprising because, I mean, you pass it the integer position, right? It's kind of like it's a pixel position. It would be, I don't know, it would be surprising. This doesn't cover addressing at all. So I don't know, it's a little ambiguous. I don't want to like spend a lot of time to figure it out. But, well, it handles MIPs, but you specify the MIP you read from, right? So you specify the position of the pixel in texels and the MIP. So I don't know. I don't think there is anything to use the sampler for. Because it's not floating point coordinates. So yeah, it's a non-issue because the extension exists. I'm assuming in, okay, so like HLSL texture 2D, what would it be called? Because load is different. So this guy gets a sampler. I'm now doubting myself, because so there is a load, but I'm not sure that this is the same thing, because in GLCell, right, there's the image 2D and then there's the texture 2D, and these are different. And the image load gets compiled, like expects a UAV type resource, so it gets compiled to like different code and uses different path and stuff like this. All right, I don't know. This is like, I guess, pointless archaeology at some point. Okay, gather. Does gather take us? It takes a sampler. Huh. So you might be right. Well, okay. Textile fetches do not support LOD or any texture wrap mode. So it doesn't support texturing, or it doesn't support filtering, it doesn't support... Maybe there's some like YCBCR nonce, I don't know. All right, all of this aligns with my understanding. I just don't fully get, and like GLSL might not have had, so these separate textures, separate images and samplers are like a more recent feature. So it makes sense that GLSL doesn't have this without an extension, without an 8-year old extension. I'm not sure why. HLSL should have, I would think HLSL has the same 3 ways to access textures. Texture with a sampler, textile fetch without a sampler, and image load without a sampler. It would be surprising if HLSL doesn't have image load. But I lost the ability to follow all of this stuff. So like maybe there's like, maybe HLSL has something that that is not appearing in the Google search. Anyway, that's fine. Okay, anyway. So I think this is good enough. Yeah, so maybe it's a GLSL spec flaw. It's just I would expect a similar thing. I would expect a similar feature in the GLSL, and I'm not sure where it is. Well, it is a mem copy type thing. There is no VK write, so I think we should be clear about the thing you're getting here. You are getting mem copy. So this nonsense, it looks like, you know, verbose and stuff, but it just hides the GPU specific functionality of, given these image objects, how do the bytes that represent a shader accessible descriptor look like? We are not using this to write the image to the descriptor heap. So this is not like the vk update descriptor sets at all. Descriptor buffer extension had a thing called vkDescriptor, vkDescriptorEXT or whatever, which was spiritually similar to this. You just use it because this just is named in like a weird way. It's fine. We actually mem copy, right, in our whatever. So this is the mem copy. Now we get the descriptor to the stack. This is just, you know, we are sort of lazy. We could cache like multiple descriptors and stuff like this in the image object. It would work. It's just you have to do it per MIP level, etc. So that part is fine. Like this is direct mem copy interface to the descriptor data. It's just, it's verbose to actually get the descriptor bytes because you have to fill like 4 structs. But you know, it is what it is. Yes, so some descriptors can be accidentally the same on some hardware. On AMD, there would not be a difference between constant buffer views and storage buffer views, I think. But on some hardware, there might be, so who knows? Do you think a software renderer running on a GPU could be as fast than traditional GPU renderer? This is off topic, kind of, well, very off topic. I don't think so. There's things you cannot beat. You know, you can't beat the hardware at ray tracing. The custom ray tracing hardware that they have is faster at doing the same ray tracing. So if you have triangles to ray trace through, hardware is going to be faster than you if it's good hardware. You cannot actually beat hardware at rasterization unless you have specific parameters. So Nanite has soft rest. it does software rests. A, it only does it when triangles are small. B, it only does it for the depth. If you remove these two constraints, it's going to be very hard to beat the hardware. So like larger triangles and stuff like that. Now you can write this code, it's going to be fine, it's just not going to be faster. So the answer is no. But if you have a very particular design of your render that doesn't need any of the hardware features, if you are doing like point splatting, then yeah, you don't need like graphics shaders, it's fine. But we are not doing point splatting. Okay, and yeah, the extensions from the render.doc, well, contributions from the render.doc author, which is cool. Okay. Okay, so I think we are done. Thank you, everyone. We kind of got most of the way there, but the samplers and some buffer plumbing remain undone. I'm gonna think about what I want to do here because the sampler code to write here isn't different now. We've done the hard parts. The sampler code, my plan with the sampler code was just to basically have the index of the sampler basically to statically allocate things such that descriptor index like number or sampler index number 1 would always point to the number 1 in the heap, in the sampler heap. And then because we only have 3 samplers and the information about which sampler to get is the statically known in the shader, you don't need. So the reason why we need this custom and direction is to have flexibility. You don't necessarily need this flexibility with samplers. So we didn't do samplers, but samplers should be easy enough. And buffers we didn't fully do, but you know, like literally you could have an if here instead of an assert. And if it's a buffer, you can get the descriptor and you can mem copy it. It's the exact same code. And there is some cleanup, but cleanup is difficult to do on stream a little bit because I'm not sure. I need to think about the structure of the code. So I'm not actually sure that we need a second stream. Maybe I'll do cleanup offline and then just, you know, there's going to be a pull request that has all of the same changes that you can read without watching the stream. So maybe that's better. I'll think about this. Okay, but by and large it's fine. We have not run into any issues other than the ones that we have created for ourselves, so that is good. Okay, thank you. And then, you know, if there is another interesting topic that I'll think about, and I'm sure I'll announce it. For now, there is no new streams planned already. So if there is new streams, if new streams do happen, they will happen at some point later when there is new stuff to talk about. Okay, thank you. Bye.